Hey everybody, welcome to Routing on Saturday. I'm Odin. This is my brain dump of 25 years of making circuits, and today will be the first episode of our three-part series making a design from start to finish. We're going to be making a temperature sensor, a Type K thermocouple temperature sensor to be exact, and it's going to use a Raspberry Pi rp2040 microcontroller and a very precise ADC analog digital converter because the thermocouple voltage coming out is very small. So we'll need a very exact one of those, and then we will start with a schematic of the entire design. That'll be today, probably mostly schematic, and then we'll get to routing the thing in the next two episodes, and Saturday after next we'll order it to be manufactured at JLC PCB. We'll get to how to design for manufacturing throughout all three. So let's dive right in. First of all, let's make a repository for our project, because that's the way things are done these days. rp2040 thermocouple, that's probably good enough. Git ignore template, we want to do keycad so that Git knows what to ignore. License, I don't care. Let's leave this private for now. Kind of ironic having a private repository and then streaming the contents. Okay, let's clone this thing. Oops, not good at hitting tab. Wait, what? There we go. Okay, now what we're going to do is we're going to use the edgy board infrastructure. Edgy boards are basically circuit Legos. They're very small circuit boards of basic blocks of different chips. So if we go to the Skunk Force organization on GitHub, oops, I can't spell. Yes, I can't spell. There we go, the Skunk Force organization on GitHub. Oh, there we go, edgy boards right off the bat. So these are, looking something like this. Circuit boards with basic functionality, and we can compose this together to make our board. So here we have finished tested edgy boards. So we want the rp2040, should be on here somewhere. It's not listed here. Maybe it's because it's not currently finished. Should be in here somewhere. There we go. Oh, it's called the Pi Pico breakout. That's why I wasn't seeing it. So we want to add this as a submodule to our repository. And because we're going to be based around that, let's see what else do we need. We need a LDO. Let's see what kind of LDOs we got here on offer. I guess I could have just searched for LDO there, but here are the finished and tested ones and all that. Okay, there we go, LDO, something tiny, SOT23 package, that looks good. So let's go add that as a submodule. Let's see how these fit together in a minute. Just going through and finding all the basic functionality that we need here. We need a USB connector. There should be some USB connectors in here too. Let's see, USB-C, USB-C waterproof. I think the USB-C waterproof one was cooler. Let's use that one. Yeah, that's, oh, look, there's even a link in it. Okay, so, yeah, that's this little bugger. We're going to put it in a nice case that's about the size of like a AA battery. And we're going to fill it up with some kind of goop, some silicone or something, so that it is waterproof, because we want to be able to use it anywhere. So using a waterproof USB connector will be cool. Okay, so I need to clone this as a submodule. Oops, not clone, sorry. Submodule, add, this guy. Is that all we need as far as UGI? Let's see, we got USB connector, and then we got LDO, and then I guess we could either, although the ADC is simple, so we'll just add the ADC directly. Okay, so I guess now we want to make a new project in our, okay, we want this to be in our thermocouple folder. Oops, I can't type. I usually just name it board because it's already in the folder named the right thing. Okay, this is KiCad or KiCad. If you haven't used KiCad yet, it's a very powerful tool. So we just created our new project, and in this new project we have a schematic editor where we can edit the schematic. Schematic is basically the human readable design. And then we also have, switching back here, our PCB design editor. That's the machine readable design, if you will. Right, so that's going to be the actual layouted board. Oh, I wonder why it's slow this time. Some of the streaming software makes everything so much slower. There we go. So I wrote down the size of the board that will fit into our standard little AA battery case. 12.5 millimeters times 28 millimeters. So let's go to edge cuts. Just lay out the board here. We want to draw a rectangle on edge cuts. And where did I say 12.5? So let's set the grid to 0.5 so we can't screw anything up. Start at one of these guys. So here we are, 12.5 times, what did I say, 28. So that's already big. Okay. 12.5 times 28. There we go, there's our board. So everything that we're going to do from now on is going to live within those edge cuts. We hit Alt 3, we can even look at our board. There it is. It's not much of a board yet. Okay, with this button we can switch back to the schematic, because the schematic's where everything's going to be happening in this episode. Beyond board and the PCB editor and the schematic editor, we also have things like symbol and footprint editor. The symbol is the representation of a component in the schematic world, in the human readable world, and a footprint is the representation of a component in the PCB world, in the machine readable world. Like if you come from a software background, Gemetic is source code, PCB editor is somewhat analogous to the compiled output, although it's not quite, it doesn't quite hold water as an analogy because you also do routing in the PCB editor, right? So you have a human input component to that part. But what we want to do first, because we have all of these submodules that we added in, and we want to compose them together to a board. This is not quite ergonomic yet because we're a little ahead of tooling with this approach. So here in our folder we have the PiPico breakout, right? Where we have some symbols. And our microcontroller sheet, and we want to copy those into the board folder. And then we have in other submodules, we've got, okay, the dot pretty are the footprints. I'm not quite sure why they're dot pretty rather than dot footprint, but that probably has legacy reasons. So put those in, and then our third component here is the LDO. See, we don't need any footprints or symbols, we just need the sheet. You'll see why this is important in a minute. So now we want to add the symbol libraries. To our design. This will take a minute. I'm not quite sure why, but KiCad holds some cache of all the libraries and checks them when you add some. So we'll add the footprints. Okay, we got footprints and symbols in. So now that we had that our design knows everything about strange footprints and symbols from the other edges, we can go in and copy some of these basic blocks right out of the other design. So here's the whole board. If you want to look at the board in the layout editor, you can see it's actually we could even do this, and you can see it as a rendered board, right? So here we have our rp2040 microcontroller with its crystal and its, I guess it wasn't a 3D model for the flash memory, but yeah, here's all the components that are needed to get the rp2040 microcontroller up and running. And if we switch back here, this subsheet is all of the stuff without the external connectors, and we don't want the external connectors. Right? So switching back to our design, let's plunk that one down. And we can just close that now because we don't need it anymore. Let's go USB-C. And this is going to be another subsheet that we need to copy in. This is the whole USB-C connector subsheet. Now the reason why this is pretty powerful with these edges is I'm missing libraries. Why am I missing libraries? I thought I added everything. This should eventually be a script, but it does all of these adding from the submodules. But the reason why this is powerful is each one of these submodules, which I'm loading in, these edgy boards, they've already been tested as a basic block. So I know that all the footprints work, and I know that the LCSE part numbers are the right part number, and so on and so forth. And this has all been tested. Put on edge. Well, I don't need that. What exactly is it? Edge footprint libraries. rp2040.pretty. I have that in there. Hold on a second. Yeah, I'm not quite sure what it's griping about, but we'll see in a minute. Wow. We can just do it manually. Oh, yeah, there's a broken library link. That's an error in the repository, so that's why that's that way. But that doesn't matter. If you copy it manually, it works. So we have our USB and our rp2040. Now we just need our LDO, and then we're good, at least for the basic design. There's our LDO. It's not quite as ergonomic as Legos, but it's getting there. I'd like to have a custom Git command where you can just, it's actually pretty easy to make custom Git commands. It's just a bunch of busy work. And you can, the KiCad formats that it saves in are somewhat human readable. So you could theoretically make a custom Git command that would just plunk down all the subsheets like this of all the submodules that you added and do all the stuff that I just did manually automatically. But now that we have them, we can do this maybe a little more logically. Okay, there we have USB, so I want to connect USB together like this. And then ground. P gives you grounds, power stuff. Yeah, just a normal ground. W is a good shortcut for wire. And then we probably want 5 volts, so let's go P again, 5V. There we go. Just to hammer all the shortcuts into your minds, I'm just going to keep saying the shortcut letter I'm hitting, W for wire. Okay, well, yeah, VDD, we want some 3.3 volts, so power again, 3.3V. There we go, enter, and then plonk that down, W. Okay, here we're doing 5 volts to 3.3 volts in ground, so let's just copy this. I do admit it was really unintuitive in the old KiCad. You could just hit C once rather than Control C to copy things. But after I got used to it, it was actually really handy to not have to hit Control. And then they took it back away because it was also just as unintuitive for everyone else. My muscle memory still just wants to do C, even though it's been like a couple of versions. Okay, got that wired up. In here should already be, yeah, the decoupling capacitors. One thing that you should watch out for that I've seen as an error a lot with USB designs is that as per the spec, I think you only have something like 20 microfarads of capacitance on the device side allowed. On the host side, you're supposed to have at least 100 microfarads, and when you imagine plugging that in, right, you're basically shorting your capacitors on your 5-volt side to those capacitors, right? So you don't want to put too many capacitors directly connected to the USB lines. And then another thing a lot of people get wrong with USB-C are these strapping resistors. You can strap CC1 and CC2 to different things depending on what kind of device you want to be detected as from the upstream side. And yeah, just look it up. In this case, we want to just be a dumb legacy USB 2.0 full speed device, so not even the high speed. So that's why we have it strapped down to ground with 5.1K. And those are coming in from the edgy, so they already have the LCSC numbers. So they, it's not just a manufacturer part number, it's actually this is the exact part for the LCSC. LCSC and JLC PCB are the same company, right? So if you want JLC to make your board and automatically mount all the components and whatnot, then it will eat LCSC numbers, which you have to feed it. This thing should also have an LCSC number. It does. Okay. So USB to... Okay, so that is basically the workhorse of our design. See how fast that went. I guess we want the ADC. So click A to add a component. I think the ADS1120 is what we want as our ADC. It's got a programmable gain array in it, and it works to very, very low voltages on the input, right? So you can set up a gain to multiply the input by 128 and then sample it. And since thermocouples are, the output's going to be in the millivolt range, it's like, some sub-millivolt amount per degree of change. And so it's very fine. The reason for that is, the thermocouple is actually like on the chemical level, a voltage difference that is temperature dependent that you're actually measuring, right? So at the end of the thermocouple, there are just two different metals welded together. That's the sensor, right? So that's, since we're kind of dabbling into the realm of physics is why we have to be so fine. Okay, so ADS1120, 60 mil, yeah, that looks like the right number. What's the difference here? Oh, that might be the, yeah, I think I want this one. So, there we go. Digital ground and AVSS. Do I want to do a split ground thing? I think I probably don't need to do a split ground. The thing with split ground, most of what it's buying you is that you don't have a voltage drop across different things in your ground plane, right? We'll get back to this when we're routing. It's easier to explain there. But if you're careful with routing, you can get basically the same effect without a split ground, but you have to be careful. That may or may not be something that you should be careful with. Same is true for the split supply. You don't want noise coming from one into the other. But if you lay it out right and do your power integrity well, you don't actually have to put things in between. Although, why don't we actually put on the supply side a ferrite or something in between there. So A for new component, R small, I like the small ones. That's an order of taste, obviously. So let's go something like this. And here, let's just do a 0 ohm resistor here to begin with, and we can put some ferrite bead or something there to isolate them if we have some problems. Select a footprint. We want capacitor SMD. Capacitor MTD. We want 603. Ferrite beads you can't get in all that small, so I probably can't get one at 402. Yeah, and then we want to, actually, why don't we put this in a subsheet? Because then everything will be nice and tidy. Oops, that's not the one. There we go, that's the one. I changed the symbols, now I'm confused. Old man. Make a subsheet, call this ADC. Call the actual file ADC as well. And put this in there. Hierarchical sheet connector is H. Let's call this GND. I like actually only using the ground and power symbols at the top level, because you may be wanting to reuse these subsheets later, and if you're using global connecting things like power symbols, then it might break encapsulation. Like maybe you might be reusing these power symbols in a design where you have a galvanic isolation between two parts of the design, and then it would be stupid if ground was just ground everywhere, then be connecting across that. So I always push everything out to top level via hierarchical sheet connectors. I mean, this design doesn't matter because we have one ground connecting, but if you get into the habit of doing it everywhere, then it helps you a lot with reusing components later. So H for hierarchical sheet, and let's do E3.3 for our power. And let's see, we want some decoupling capacitors. Sorry, C small. C small is a good one. Where do I do these up here or something? What would look good? Well, I drag this up. G is a good key to drag things with. I don't know what happened there. So G and then drag it, and then we'll do G here and drag that over. And then we can do M to move components. Hammering all these shortcuts into everyone's head. So this should be something like 10 UF. Actually, why don't I just copy it from the LDO, because then I will get the LCSC number coming along with it. Oh, but those are 0603. I'm going to have a pretty dang small board. I think I won't need to change all of these 0603s around. So why don't I do that first before I start copying things, because then I'll have to do it multiple times if I copy it, right? Oh, sorry, just to tell people what I'm actually doing. This button here is all of your components as a spreadsheet. And so if you want to change multiple components, oh, it doesn't really fit on the screen, but if you want to change multiple components at once, or properties of multiple components at once, this is a really powerful tool to do that, because you can do them all. So let's see. I guess I don't want to see if it's do not populate. And I don't want to see if it's included from BOM. I don't want to see if it's included from board. Footprint I do want to see, and I do want to see it bigger. Okay, so I got everything as a... Oh, look, the LCSC numbers didn't come in for everything. I wonder why that is. Doesn't matter. Yeah, so I want to make all of these smaller because we have some constraints on the sides of this board. 12 pico, that'll definitely work in an 0402. You do have to watch out with some of the bigger values if they'll be available in that small of a package, but since we don't have a whole lot of voltage going across these things, you can get up, 10 micro, you can still get that in 402. Let's see, we could actually even go to the LCSC thing. Make sure we can get them before I do everything. Okay, yeah, 10 volt is fine. 402, that looks good. They're not expensive at all. Look at that. And they're half a cent if you buy a lot of them. It's amazing how cheap components are. Look here, some that are even cheaper. Quarter of a cent. Yeah, okay. So let's go with 402 all the way up to 10 micro. We do need to take the SC numbers back away here in the components that we made smaller, because otherwise we're going to confuse ourselves, because that component won't fit on there anymore if it's that small. Okay, let's make this one small too. Resistors definitely be available in that size. It's funny, the 0201 in metric are 0603, and so you can, I remember the first time I accidentally ordered one of these rather than one of these, and was just blown away by how tiny it was. And yeah, the 0201 is too small to hand solder, but 0402 you can hand solder those if you screw it up. Just use enough flux and it'll work. Okay, we did want to leave this one in that size. Oh, we definitely want to get rid of this because we made it smaller. Okay, so it didn't actually help us all that much that all the LCSC numbers came in through the, geez, why didn't that one come in? I am a little confused. Did I clone an old version or something? Oh well, we'll fix it in a minute. Yeah, okay, I think I got all the components to the right size now. Let's get up out of here and into our, oops, yeah, I want to clone, no, not that one, sorry, from the LDO page. Clone this so that we got all the same properties going. use this as decoupling here and here. One should be enough. Like, if this was a design where I wasn't space constrained, I would use both 10 micro and 1 micro, just to make sure I'm swallowing all the different noise frequencies and whatnot. Although some of the reason you do that is because these smaller components will have smaller parasitic inductance and whatnot. But that usually has to do with physical size. Like, I mean, I guess it's intuitive. If it's actually physically a bigger thing, it will take more distance of going through stuff to get to the whole chip, right? And getting through stuff always has some parasitic inductance, right? But since these little buggers are tiny anyway, I mean, there is a more complex structure in the 10 microfarad capacitor than in the 1 or 100 nano or whatever. So yeah, it would probably be better to do both 10 and 1 here, because then we're swallowing all the different frequencies of noise. But we are space constrained on this design, and yeah, it'll be fine. I know that seems to be becoming my tagline for this, but yeah, I mean, you don't want to over-engineer it. There's a few things that one always wants to get really, really right, and everything else is usually not all that important. So you don't want to over-engineer everything. So I guess I want analog coming out of this. So H for hierarchical. And 2, I think I'm going to measure from between A and 2 and 3. Don't ask me why, but I remember this chip has different ways you can set the multiplexer and programmable gain array. So not all combinations work. And I know that 2 and 3 work with the super high gain stuff. I think 1 and 2 also do, but I'm sure that 2 and 3 do. So I'm just going to do 2 and 3 and done with it. Oh, we definitely need the entire SPI bus. So we need CS. H, we need, so data out, that would be master and slave out, right? MOSI. Because it's out here. Ah, ESO, sorry. Master in, slave out. Data in would be MOSI. I could have just moved it rather than correcting it. Oh well. I just want to make that symmetrical, and then clock is going to be clock. Do I want to actually connect data ready? I think so. Oops. What's the difference between this clock and that clock? I'll have to look that up in a minute. I don't have an external reference, so Q is in quiet is the way I remember it. I'm not sure if that was what they were thinking, but makes it a no connect. And I don't think we're using either of these either. I guess we could have done hierarchical sheet, brought them to the outside and then made them no connects there, but data ready, I'm just going to call data ready int. Int out. nah, maybe I should call it data ready so people know what I'm talking about. We are going to need that top level. I'm not quite sure with the clock. You know, I'm just going to look at the data sheet. Maybe I should just look at the data sheet. Data sheet to the rescue. You can tell I didn't prepare for this. Okay, SCLK. And the other is, oh, that's clock output, right? It's got its own internal oscillator and it's, oh no, that looks like an input, but if it's got its own internal oscillator, I don't think we actually need to connect it. Okay, digital input, yeah, okay, so electronic clock source pin connected D ground if not used. Well, I definitely don't want to be putting an external clock on this board, so we are not going to use it, so we'll just connect it to ground. Okay, I guess while we're at it, we can look if we need to connect the refs to ground as well if we're not using them. Input, negative reference, input 0, positive reference 1. Don't have a reference, so what do? Do I just leave them floating? I think I can just leave those floating. Hold on a second, I think I can open something on a different. Yeah, no, I'll leave those floating and I'll check later when you all are not waiting for me. Make sure that wasn't a stupid move. But so we created hierarchical labels inside the subsheet. If we want them to pop up on the subsheet, we gotta connect them here. So AN2, that's our analog in, and then here. Well, I guess I could rearrange them later if I get it wrong. Ground down here. So mostly 0.3, we'll do all the way up at the top. Okay, that's all of them. Let's move this over to an SPI. Do I want SPI 1 or SPI 0? That's a good question. I'm going to go with SPI 1 just because on the networky stuff, I use a lot of SPI 0 for the network chip. So if I want code to carry over, although it doesn't really matter, it's a strategy pattern anyway. Oh well, rambling. Let's see, why don't I move this up so that there's a, or I guess I could just put the power on the other side. That would actually be even more compact and logical. Get these into some logical order. 1, 2, 1, 2. And then okay, and then on this side, want okay, we want, let's see, TX and RX are up at the top, so let's so TX would be master out. I'm not sure why I didn't label those MISO and MOSI. Must have been in the phase where everything was being renamed. Okay. Clock. Now, okay, there we have chip select. So GPIO 14 or 15 for data ready. I think we can have pin interrupts on anything on the rp2040. So why don't we just do this? Connect those over. This way we can see top level what's going on quite well. Okay. Okay, so we have USB connected to the rp2040 microcontroller, connected to analog digital converter. We have our LEO. So now I think we just need the analog front end circuit for the thermocouple. So what do we want to do? We definitely want to bias it so we can tell if nothing's connected. And we want to have some resistance between us and the outside world, just so that we don't get fried immediately if somebody connects it to something wrong. And I guess we probably want to filter out some high frequency noise. Although that shouldn't actually be all that bad because all the noise should be affecting both the lines at the same time. So why don't we just start laying down components? So I want a low pass filter, just you know, an RC filter. Let's go with 10 nano or something. Oops. And then footprint, we want a tiny one. Capacitor. SMD, there we go. Okay, and then I guess I want to go to ground as well. So why don't we go like this. And then I want to do the R as part of the RC filter. Okay, what do I want? Ohm is probably enough. Make it small. Something like that. I think I'm just going to do test point pads to begin with because I don't actually have the footprint of the connector, and I'm not probably actually going to even use the footprint of the connector. I'll show that to you guys next stream, what the connector looks like and how I'm actually going to solder it on there. Because I'm not actually going to use it the way it's supposed to be used, which, famous last words, right? But, so let's use just a test point as a stand-in for the connector. Oops, the streaming thing on the program is slower, so it's messing with my intuition of how long I have to wait between keyboard shortcuts, which I hate it when you get faster than the program. Okay, so we still want to bias this so that we know if something's connected or not. I'll show you what I mean by bias in a second. So we're going to do one up, and let's do something huge like 10 mega ohms. Oops, don't want that little hat there. Okay, I blame the French for that symbol. Anyway. Excellent. Circumflex, which sounds like a bodybuilder move. The circumflex. I'm sorry, non-French speakers have no idea what I'm talking about. Not that I'm a French speaker or anything. They tried in school to teach me French and they failed. It's not even my fault. Ha ha. Okay, so if we connect this like that, and this like that, and then this like that, then there will be a very slight amount. I mean, imagine TP1 and TP2 connected to the thermocouple. Then there will be a very small amount of power flowing like that through the whole thermocouple. The resistive voltage drop in the cables is going to be nothing at 20 mega ohms, right? But if nothing is connected, then it'll give us then TP1 and 2 will not be connected together through the thermocouple, and one will just be 3.3 volts in the other ground, which is higher than the highest plausible voltage you could get out of a thermocouple, and so we know nothing's connected, right? So that's why we put the two 10 mega ohm resistors on there, so we can detect if something's connected or not, because otherwise we'd be like giving garbage data when nothing's connected. We don't want that. We want to be able to detect it. So I think that is, I guess, do I actually even need these guys? Oh, I probably don't need these guys, but I do need something else. If I just leave it like this, people who have been burned on the stream will, oops, I selected the wrong thing. Let me put this up so I can see if anyone's chatting with me. I don't know if the chat is broken or if no one ever chats with me. Like the first one I got chats, and now I haven't gotten any chats, which is weird, but I guess it doesn't matter because people message me afterwards, usually with questions anyway. So message me after and tell me if the chat is broken, if you tried to chat with me and it didn't work. If we leave it like this, then our AN 2 and 3, right, they're going out through here to the thermocouple. And the only thing kind of holding them in range, if you will, of the ADC are these two resistors, which are 10 mega ohms, right? Since this is a cable going off through the world, the common mode as in affecting both lines the same interference is going to be pretty high, right? So 10 mega ohms is not enough to keep that in range. So why don't we pin one of these two? I'm just going to steal this and give it a different value. Let's do, I don't know, what, 10K? 10K should be good. Connect it up like this. W again. So R12 and 13 are going to be giving us a voltage divider, which is going to pin AN13 at a specific voltage. In which case I don't need this anymore, right? I mean, that's not going to do anything if that's already pinned to specific voltage. So just the pull up here, or I could actually do this top one down. Seems somehow more logical to me. I don't know why. Yeah, because that way the high pin will be lower than the low pin. Because if we make this like the positive side of the thermocouple and this is the negative side of the thermocouple, we'll be pulling the positive side way down below the negative side, and that will be the most illogical input value. Yeah, I think this will work pretty good as a input circuit for a thermocouple. And we probably could do more than an ohm here, but it doesn't really matter. Okay, what we still need to do is we need to protect ourselves from ESD. Now the edges don't have any ESD in them because that's a whole design consideration thing, right? So they can't really, by definition, have the right ESD because they don't know what else is going on in the design and what's connected to the outside world and how and why and whatever, right? So, coming across USB, that's not a wire that's going outside. So if you're doing, or not going into cable channels, not connect to mains, any of that stuff, so you're not going to have to survive a surge or burst test on that. You just need to survive ESD test. So this design is, from an EMC perspective, is EMC is electromagnetic compliance. It's the the tests that like the FCC and whatnot require you to do, or whatever country you're in, it'll be a different entity, but require you to do to be able to sell products. So we want to pass those. And this one's a lot easier than the network switch that we did last week because it's just USB connection. So we just have to worry about ESD and not making too much noise to the outside world that we might interfere with other devices. So I guess right here on the input lines would be a good place to, so I'm just going to use G to move, oops, did I hit the wrong button? G should actually keep them connected. What's the deal? I guess G doesn't work for multiple components. That's weird. I didn't scooch it right. I got so many messages after last stream about using the word scooch. I guess it's not a word, it's slang, but it means to slide. And I somehow use it all the time with PCB stuff. There we go. Okay, so let's move this all. I guess, no, that's enough room. Let's see. So A to select a component, so USB LC6 or something. Let's see if that's actually plausible. USB LC6. Yeah, 2SC6. So 2 data lines, SOT236. That sounds right. So the considerations that we need to take into account with the USB data lines is that we can't have a whole lot of capacitance, otherwise we're going to screw up the signal, right? So we need clamping diodes like TVS diodes to deal with potential static electricity. ESD, electrostatic discharge, basically means somebody touching it who is charged up in some way. Maybe they were jumping on a trampoline or have an acrylic sweater and hair or whatever. So they're at high voltage and they touch our USB connector, and we have to make sure not die because of that. So that's the ground, and this one's 5 volts. We got the 5 volts clamped that way. And then we got the data lines together. No, not together. Wait, so that's pin 1 and 6. So do they want us to actually go through the chip? I actually don't remember going through the chip. I mean, that would actually make a little bit of sense, because then you definitely couldn't have, you couldn't do it as wrong on the downstream side. But why don't I look at the data sheet here just to make sure I'm not doing this wrong. It's been a while since I've done one of these. I've been doing mostly network stuff, which we will get into more at some point soon. Okay, so this is the layout. No, that's the test board layout. So how exactly am I supposed to use this? Are they expecting me to go through the chip? Well, that looks like it's definitely going through the chip. Yeah, here we go. Yeah, so we're going through the chip. I hope the chip is, what's USB again? 90 ohms. 90 ohms of wave resistance? Oh, they probably made it 90 ohms. Otherwise, it'd be stupid. Okay, so I guess we are going through the chip here, which means we can make this a little more logical here. Why don't I make it like this, and then pull this up like that, and then it's all logical. Okay. And then since I already have this, I think I'm just going to use this for the thermocouple side too, because in that case we also don't want to have too much capacitance. I guess I'm going to do 5 volts here. The input should be 5 volt tolerant, and they're through an ohm of resistance, so that should be fine. And I'm not going to go through on this side, just because if I put it in the right spot, it'll work anyway. Something like that, so that we can clamp the 2 inputs to somewhere between ground and 5 volts. Yeah, that should work. I'll just have to, in the layout, make sure and put this in the right spot. Does it already have a footprint? Yes, it does. Okay, that's good. Okay, I think we're about done with schematic in an hour. Wow, that went fast. So, let's pull it in here and see what it looks like. Well, I guess I had some errors. Let's see, what are the errors? Error TP1, TP2, no footprint signed. Okay, that's solvable. I think I want to just do big old pads. Test point, not a bridge, not a loop. I just want like a big old pad, 3 by 3 millimeters. That seems about right. I use it for both of them. Put that in. Yeah, that's about the size I wanted. Okay, so let's start with USB and then work our way across. Now this line means that's where the board edge needs to be, so we're right about the right spot. I think I'm going to make it a smaller grid, plunking this stuff down. Yeah, I want it to stick out a little bit further than the board, just so that the board kind of disappears in the goop. Oh, my mouse hand is not steady today. Okay, so another advantage of the hierarchical sheets is you can just click on the sheet here and it'll highlight everything that's on that sheet, right? So you have the logical what's what already. Okay, and then this is the analog stuff. Oh, I guess this is power. Yeah, power is going to go up there somewhere. And then, oh, these are the EMC thingies. So this needs to go close to the USB. And this one needs to go close to the test points. Should I actually maybe connect it through? I am torn, I tells you. I guess I just go around. Yeah, it just somehow seems weird to me to connect it through on something that's not actually USB, although I don't know why it's weird to me. Okay. So let's do the test points just as far as they can go. Something like this, because there's a big old connector that's going to be soldered kind of flat laying on top of. You guys know what a thermocouple connector looks like. There's going to be a big old thermocouple connector laying flat across those things. Okay. So let's see, what am I going to put on the top and what am I going to put on the bottom? Am I going to do high-speed stuff on the top? Well, if I do the data lines like that and then into this thing, then I don't really have room. And I do need to do the ESD stuff right away. So I want to put this stuff on the bottom. Well, I'm probably going to do the decoupling caps on the top, but oh well, we'll flip those later. So the microcontroller is going on the bottom. The ESD stuff's going here on the top, I think. I guess I could put this on the bottom too. Something like that. Okay, well then those are switched around, but I can put the data lines wherever I want to. Because I still have another, yeah, there. I still have to do the ADC somewhere. And so this seems about right to me. Oh, and I also need to do the LDO somewhere. So I could also put the LDO underneath the connector. Well, I guess I do have enough space generally. Why don't I put this thing right here? And then this maybe just a little bit so I have room for vias around the outside of that thing, or maybe like this, so I can do vias like down in here or wherever. And then strapping doesn't need to go very close. LDO doesn't need to be close. So I think we got all of the, oh, okay, this guy needs to be close to those pins, because this is probably the most important part of the whole design, getting these guys right, because these are going at 133 megahertz if I remember correctly. Now 133 megahertz is pretty fast. It's USB high speed is 400 something megahertz, I think 480, but we're not using high speed on this design. We're using full speed, which is I think 12 megahertz, 12.5, something like that. And so, yeah, 12.5 megahertz, that's a wave distance of like 10 meters or something. And then the, through copper on a PCB, right, the speeds are going to be dependent on what medium it's traveling through. But 133, that's like less than a meter. And then you got to, like, it's not going to be a sine wave going through. So you're going to have frequency, parts of the frequency of the bits going through that are, rule of thumb is maybe 5 or 6 times higher or something than the frequency, because the rising edge is faster than a sine wave at that frequency, right? So yeah, that's what, 20 centimeters or something. It's still a lot longer than the tracks that we're going to be using, and that saves you a lot, right? If you're considerably shorter than the wavelength of the highest frequency, then all of the reflections, like the initial reflections that you cause by screwing up or changing the wave resistance and whatnot, those will all have reflected back and forth a bunch of times before you get to like the middle of the bit. And so that the problem with reflections, where they do come and bite you, is if you the other side sees rising clock, okay, waits half a bit, samples in the middle, and if you have a reflection of something right there that brings that part down and to make a 1-bit 0 or a 0-bit 1 at that point in time, then okay, you're going to be corrupting your data, right? But if things are reflected back and forth like 100 times, because that's how short the cable, the wire is, by the time you get to the middle of the bit, then yeah, it becomes very forgiving, right? So yeah, that's why longer wires you have to get it more right than with shorter wires. Shorter things save you in a lot of situations. But I still want to make this beautiful. Okay, how do I want to maybe go up like that? So that would be, now that'll be hard to route. So going, how do I usually route these things? Okay, well this should be easier to route. Something like that. But what if I do it like this? Yeah, that should be. Well, that's going to be a little bit ugly because this blue thing here, this is actually a physical hole in the board where one of the guide pins from the SMD connector goes through. Keep it from, keep it from scooching around while it's getting soldered. To make sure it's at the same spot every time. So I can't go higher than that. So if I try and route that, then I'm going to be having, although I could just do USB from the back and then everything's good. Why don't I just do that? Predefined size. Let's see, what is the JLC PCB? I haven't looked at this in a while. What's the smallest track that you don't have to pay extra for? So rigid PCB, okay, layer count, blah, 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 blah. We want traces. Min track width and spacing for 1 ounce. 1 and 2 layers is this. Multi-layer is 0.9 millimeters. Holy shit, they got better. That's better than I remember it. I remember it like 0.13 or something. So they got better machines or something. So yeah, we could do 0.1. I think I'm still going to do 0.13 just to not be super close to the tolerance because we don't need it to actually be that fine of a pitch. So why don't we do 0.13, and then I like 0.2, and then let's do 0.5 for powery stuff. And we don't need anything bigger because we don't have any major current flowing. I guess they want a via diameter and hole. Let's see, what do they want us to? Annular ring. Okay, that will be 0.25 millimeters or above. 0.25, that would be 0.5 because it's on both sides plus the hole. Where's the hole? It's hole spacing. Where do they have the hole width? Drilling. That's why I'm not finding it. Drill diameter 0.15. So let's get this set up. So the hole is 0.15. And this is what? Total diameter? So this would be 0.25 on both sides. So it'd be 0.65. Let's see if that looks right. Yeah, that looks plausible, like the right size of a VI. Definitely want. Okay, so that's 0.2, something like that. Yeah, okay. So got that set up. I usually use a template which has that in it, so it's been a while since I've set this kind of stuff up. Okay, so let's root this and make sure this all works before we... Oh, wait a minute, I still have to set up spacing. That is in here, I think. Okay, constraints. Minimum track width. 0.1. Minimum clearance would be 0.1. It was actually 0.09, but let's not be too close. Annular width, that was the 2.5. Via diameter, the 6.5 that we calculated out. Now this is going to depend on, the capabilities of your manufacturer. So you're going to set this up based on whatever your manufacturer can do. Press looks okay. So let's see if, oops. You select all of it so we can get rid of it. Okay, so now I want to connect this guy up to that. So did I set up the widths wrong? Or the clearance or something wrong? Ah, here we go. It's in the net class. I don't really use net classes. I'm not quite sure. Yeah, I don't really use net classes. I mean, I guess on a really big board where you have like different nets that do different things, if you're doing like power nets or something. But yeah, I usually just know what's going on anyway, so I don't have to do all of that kind of stuff. But I guess it might be an important tool for some designs or some team architectures or whatever. Okay. So that's ground, so I want to leave enough room for a... Well, I'm not going to have enough room for the rest of these nets. So I want to move this. Hey, I didn't say scooch. There we go. leave enough room for the via to ground there. Oops, I want a D and not G. There we go. Okay, and that is plus. Okay. So looks like that is connected pretty well. Not enough room for a via. Move these down. That does look like an odd via. Did I read something wrong here? I have something like a via, not very blind vias. And via hole size diameter. Hole size 0.15. Okay, got that right. Via diameter. Okay, that's weird. This is, I guess, the full diameter. Yeah, it looks like starting with a 2-layer board. I mean, why would you even have a via on a 1-layer board? I'm confused. But anyway, yeah, so I definitely set this up wrong. I don't know how I got to values that I got to. I misunderstood something, I'm sure. But if they say a whole, a via total is 0.25, then let's go with that. Constraints, and via diameter, angular width. I'm not sure how they get to this value. But predefined sizes, then let's go with the the hole is 0.15 and the total via diameter is 0.25. I'm reading that right? Via diameter 0.25. Okay, well those are smaller vias than they used to be able to do. I was getting worried that they got worse. Okay, so let's get rid of this via and make a new one. See what it looks like now. Well, now that is a much easier via to deal with. I think I'm going to make them a little bit bigger. Sorry for optimizing the crap out of the constraints here. Like I said, I usually just use a template. JLC template project. Wait a minute, that doesn't look like it got bigger. Did I do something wrong? Did I do something wrong? No, I didn't. Well, I guess that was just... Okay, so... this thing probably comes with a capacitor, decoupling capacitor. Let's just say C1 is its decoupling capacitor because it looks like these are all the same. Let's go something like that. These tracks are so tiny you can even do it like this, but still want to make sure that connected to ground. Oh yeah, we want to set up the ground layer. So I guess, I mean, we want to put the ground plane right, like as far as board stack up goes, right close to the layer with the high frequency stuff. Now we got high frequency USB on the top. We got high frequency connected to the flash on the bottom. But on the top, our USB connections are going to be super short anyway. And they're not going to be the right wave resistance anyway. Oh, this is unfortunate. Do we maybe want to switch around the polarity of this thing? Like, M up top and P down low, so that they're going through the other way around there. That probably should work better, I hope. Either that or my brain is playing tricks on me. Because I know I've designed things where this just worked. I'm not quite sure. Yeah, now this just works. Okay. Now the reason why there's two DM and DP pins is because the USB-C connector connects both ways around, right? So there's actually literally two sets of things in the cable, two strands of each. Yeah. So you can actually detect which way around the cable's plugged in. So you could actually literally make a USB-C connector that will always be the wrong way around the first time. You always have to unplug it, plug it back in the other way around, just to make the people go crazy. Anyway, okay, so that works now, and then we're going down to the bottom here. So like I said, there's not that much here, which is this is not that long. Now I could be kind of trying to get wave resistance right here and whatnot, but these are just so short that it's not going to matter. Like, I can't really, I mean, going through the chip, through the pins, well, that's going to be the wrong wave resistance anyway, right? And going through the USB connector, well, that's probably going to be somewhere close, because otherwise it shouldn't have become a USB connector, right? But it's also going to be wrong. And so, I mean, how are they going to tune it to 480 and to 12.5 and to whatever low-speed USB, because nobody ever uses low-speed anymore. It's just legacy. But theoretically, there's a huge range of frequencies they'd be going through those pins. And so it's probably tuned to the wave resistance of, to the 480 anyway. Yeah, let's see. I don't think it matters. It's so short. It'll be fine. Like if we had, 20 centimeter long tracks going across the board, then it would be important, especially if we were doing the high speed USB stuff. But we're not. We're doing. There's a siren going on outside. I'm in an industrial park in the weekend in the middle of the night. There's a siren going off. Hopefully nobody's going to come break down the door and try and steal my stuff here. Okay. This Looks good. So that means we have almost all of the high frequency stuff on the bottom layer, which is different than last week. So let's do our ground plane. Oh no, I didn't even make it a 4-layer board. Hold on. That is here in the physical stack up, I think. Yeah, there we go. 4 layers. Now there we go. So bottom, and then the lower inner layer and the top, those should all be ground, and then we'll use the green one for power. Although, wait a minute. Yeah, I was talking to you guys about splitting up the ground planes into digital and analog. So ground is 3, 4, and 5 here. So it's just analog and digital right next to each other, I guess. Analog is the 5. Well then, we put the chip something like this and then made the ground plane like stop here, then there'll be one connection between the two, and we won't have any power flowing across, any voltage drop flowing across that part of the design, right? And there's not going to be a lot of power flowing anywhere anyway, but yeah, so we might want to adjust the ground plane later just to play nice with the analog, but I'm just going to leave it like this for now. Okay, so we got ground set up. Oh, I don't have any via, so that's why it's not showing up on the other layers. And we're still working on it. Plunk down a via here, and then we'll flood fill everything. That actually looks like way too much distance. I think we got something wrong. Clearance, yeah, okay. If we have a clearance of like 1 on the board and 0.5 on the ground fill, that's gonna not so well. So, okay, thermal relief gap. Let's just leave that like this and see what it looks like. Okay, that looks a bit better. Okay, we got a big gap to board edge. I don't think we need that either. Where is that? Outline hatch. Oh. Why do we have such a big gap to board edge? Guess it doesn't really matter. Okay, well, let's turn these off now that we got them working somewhat correctly. Okay, so we still have an LDO to put somewhere. And we have, is the LDO going to fit on the bottom under the connector? Not really, that's a little too tight. So I guess it's going on the top layer. And these guys, that's too close to board edge. Why don't we just do it like this? Although I probably should do power integrity first for the microcontroller. So, where is this one going? Yeah, so this is going to be this direction. Am I stupid? What's the deal? Oh, that's ground. That's why I'm being confused. Put this like up like that, because we're going to do, oh no, do we want it up or down? No, we want it down, because we want to be able to connect to this guy with the whole SPI bus on this layer. Getting things somewhat situated here. And then there's going to be a resistor. Where's the... look at the... Now, do I need all of this crap? think anyone's using ADCV ref anyway. Because I'm not using the onboard ADC. No, I'm not using that anyway. So I could actually save myself some components here. No need for this. Just connect it up like that. That's not what I was originally looking for. Anyway, here we go. This is the resistor, and those are the capacitors that I want to see here in the design. Yeah, those are the... Oh! Move things too far around. Okay. So this is connecting like that. Well, we could just plunk it down like this. And then... Now, I don't think we have the programming connector set up yet either. I think it's going to go like here. So maybe we want to move the crystal up a little bit. To something like this. Okay. Let's see what we got there. Those are all no connect. Run is going to, yeah, that's the reset, if you will. Did we not name that net? How naughty of us. Let's see, run. Oh, it should be named. Why isn't it named? Did I just look wrong? Yeah, it's named run. I'm just blind. There we go. So yeah, so that's like a 10K up and I think 1 nano down. Is that the only 1 nano that we have on the board? Otherwise we could make it a 10 nano. Yeah, let's make that a 10 nano and then it's got friends. Because it's just stabilizing the run pin, which is just pulled up anyway. So we want to start running as soon as the power goes on. Run until the power goes off. Okay, but that doesn't need to be close to that pin. And I think run is going to be connected to the programming connector anyway, which is going to be over here. So that doesn't need to be close. So, yeah, SWD, SCK, those can go down and around. I guess maybe I do want to move the crystal still again, because I don't really have room for vias there. I could go back here and then vias in some middle area. Yeah, that'll work. Oh, but I do have VCC and VREG out, but I think I'm going to do those on top. So, crystal like this. Oops. Is that important? Well, yeah. We'll make it pretty. Wait, that's ground. Okay, there we go. Okay, so we got 3, and then this is probably some, yeah, VREG out is some internal regulator. So what do we got? 2.2 probably is going to go close to the VREG. So let's put that on top. That's going to go to close there. Something like that. And one of the 3.3 volt ones, 100 nano. Yeah, why not? Make the 2.2s right next to each other. It doesn't really matter. You just gotta go somewhere. Okay. Those are tiny vias. JLC must have stepped up their via game. Okay, now we have ground here. That just needs to be via'd off to the ground layer. And we have GPIOs and all that kind of stuff. And then we have, here's the next power integrity interesting thing. So, I guess we could do that. We don't really have anything up here that we're connecting to anything, so we could do that on the lower layer. Something like that. Wait a minute, did I not correct ground properly? Yes. Okay, so that's why I was being so confused. I forgot to connect ground. Now things should be better. Yes, now they're called ground and everything. Oh, being stupid. There we go. Okay, so what's the next power integrity-ish thing? Here we go. So just grab another one of these 100 nano. It's the next power integrity-ish thing here, I think. Yeah. So should I do those on the bottom? Yeah, I think I want to do those on the bottom. There are three pretty close to each other. How many more of those do I have? Oh, I have a bunch of those still left. That's probably more than I actually need. But let's just start lining them up down here. Got a lot of that kind of pin down here. Let's see how many we have extra at the end. Don't want to be too close to the edge of the board, especially with something like that. Like here, yeah, whatever. Because if you want to score your boards, which is when they do like a V cut from the top and from the bottom, where you can then just break them apart, that's the cheapest way, rather than with a router and then have to have like mouse bites where you can break them apart. And that's a headache, and it's uglier. So yeah, we want to score this one. And with scoring, you don't want to be too close to the edge, because then otherwise, like there's like a physical, looks like two pizza cutters from top and bottom to break them apart. And that tool is going to need a little width to fit through, so we don't want that bumping into our components. And since this board is so small, it's kind of unintuitive, like how close these things are still, right? Like this is the edge, and so that's half a millimeter, even though it looks like a big space right now. Okay, so yeah, there we have another just normal 100 nano going down there. I'm going to connect them all together on a plane here. Am I too close? Yeah, I think I'm too close to the pad there. As I explained in the last couple, if you have your vias too close to the pad, then there might not be solder mask in between the via and the pad, so you might have solder paste running down into your via, and then it doesn't solder well to the component. Then you have to buy the more expensive vias that are plugged so they don't have a hole in them, and then it works. But yeah, it's something to watch out for, because it can work and then no longer work, and those are the worst kind of errors, right? If something breaks all the time, you'll notice. And if something never breaks, well, then it's not a problem. But if it sometimes breaks, that's when it really gets you. Okay, so this is, I guess, whether it goes here or one further down is going to depend on whether I have capacitors left over on the 3.3. Oh, it looks like I don't. Okay, so everything's cool. VRig out. Well, where does VRig out connect to? Oh! I guess I'm doing those up top because I already set the other ones down low. So let's put it like this next to that guy. Like that or so. And there should be one more of those. Let's assume it's this one and see if we turn out right. Yeah, it is. Okay, so we're going from there. Yeah, let's put this just on the other side here. Try and line it up as far as the x-axis, although that's just for pure aesthetics. Has nothing to do with working properly. Again, with our power loops here, the chip is running at 133 megahertz. 133 megahertz is like a meter wavelength in speed of electrical propagation through copper on a PCB with all of that. So yeah, I mean, this does look long, this power loop here, but so we're going from the pin to here and then around to here, and then so the whole thing's going to be maybe what, a centimeter? And if we do the same times 5 rule for the high frequency components of the switching, that's 20 centimeters or something, and we're at 1 centimeter. We're still good as far as power integrity. It's just not intuitive because everything's so small here. Okay. This is going to be an important via because we're burning off the EMC there. Okay, I guess that 5 volts is not that important right now, so why don't we finish the power integrity stuff. What are these guys? Oh, okay, these are for run. So yeah, I think we got the power integrity stuff pretty well squared away, so why don't we put the LDO here, or up there, I guess it doesn't matter. We'll put it down here. And then what are all these? Oh, these are my low pass filter stuff. These is the analog. And these are the coupling caps for the ADC. So why don't we place these next? So all of those are going to the bottom, although still I think I'm going to do that on this side. And then decoupling caps. Like this. ADC is running at a far lower frequency than the chip, so not as power integrity dependent. Why don't we make these fatter, at least relative. 0.2 millimeters is still pretty small. Okay, we're coming up to pretty much end of the stream here in 10 minutes. I'm amazed at how far we got. We might just need 2. I think we only need 2 episodes for this thing. Next time I'll go into the part ordering, or PCB. We'll order the PCB at the end, and then before that we'll finish the routing and stuff, and maybe talk a little more about design, and then that episode will be full. So Yeah, we got through this one really fast. So these are all going to go on this end. To do the filtery stuff. And LDO there-ish. Don't want to get too close to the edge of the board. These are the decoupling for the LDO. Oh, I think I'm going to spin it around because I don't want 5 volts to go all the way over there because we don't need it on that end of the board anywhere. We'll do 5 volts to ground here. I guess we will take a bit of time getting all the silk screen stuff in the right place and whatnot tomorrow. Although that might be a little boring. Silk screen is just busy work. Okay, these are all going to have to go there. My rule of thumb, anything going through a resistor is not going to need to be placed really close to anything. Well, why don't I start at the top with this one. Oh, so it's saying the chip goes all the way to there. Yeah, that's fine. Start at the top with this one, and then as the next one, okay, that's the far away one. We can actually just put that all the way up here. I guess we could move that via and try and go behind that. Something like that. And then this one here, go around the back. I guess we can't fit between the hole and there, but that's fine too. Yeah, I hope you guys all had a good week, a good Saturday. Looks like we're right about done here, so you have a nice rest of your weekend. Again, all anything you liked or didn't like or want to see or don't want to see or whatnot, put it in the YouTube comments or on X. Either message me or publicly or as answer to this. I don't mind. I'm still just figuring out how the most effective way to dump my brain and my experiences. I learned a lot from just watching people do stuff in the beginning of my career. That was always kind of the most enjoyable way of learning for me. So that's why I'm kind of trying to help people emulate that. Oops, I got way too close with this via. I want G because I want the tracks to come with. Is that what I want? Yeah, that'll work. Yeah, so I figured you guys can all watch me do stuff just like I watched other people do stuff. I mean, back then it was in person and it wasn't that often. This kind of thing would have helped me a lot way back when. But if you have any ideas or anything specific, then don't be shy. I'm just trying to pass some knowledge along. And I don't really mind what format it's in as long as I can do it. I'm still pretty new to the streaming thing. I guess I could just connect those like that. I don't need this. Yeah, the rp2040 is a good microcontroller. It's yeah, the onboard analog digital converter, they screwed that up. So that, yeah, that's, I wouldn't suggest using that. It's got some weird problems. But everything else, especially the software tool chain, is built like a modern software tool chain, which is not common for microcontrollers. So I have, and the programmable I/O thing is cool. PIO, they did good with that. Do I really want to make 5 volts this fat? I don't, I guess I don't really have any disadvantage for making 5 volts that fat. Yeah, we got through this really quickly. I thought we would take way longer. But yeah, that's the advantage of the etchy boards. We use them in almost all of our products at this point. You know, the design, build, test loop is figure out which composition of etchy boards will yield the product that the customer wants, and then build all the ones that don't exist yet, test those, and then compose them all to the big design, and then route that, have it produced, test it, and yeah, there's still usually 1 or 2 bugs in that, but you know, as you can see, you know, we had all the edges already existed. Actually, funny enough, the ADC also already exists as an edgy. I just wanted to show some actual making a hierarchical sheet and stuff in the stream. So theoretically, we didn't have to build any of this fresh. So yeah, that's the power of the edgies. They are open source. That Skunk Force organization that I downloaded, you know, that I added them from as submodules, is an open source nonprofit, which I founded with some friends, or some friends founded with me. I actually did way less work than a lot of the other people, so definitely don't want to steal any thunder there. But yeah, that's our nonprofit. Yeah, they're all MIT licensed. I try and do everything MIT because I understand it's the easiest for people to consume. Yeah, so I guess that's the end of the stream. You can just watch me routing the rest of the SPI bus while we run out the clock. But yeah, see you all next week when we actually order the thing. And then I would love to hear comments about what people want to see later is the next stuff. I think we could maybe do an Ethernet device side, because we did the Ethernet switch and the power over Ethernet host side, so that the switch side of the power over Ethernet. And we could do a power over Ethernet power device side with Ethernet and a microcontroller. You know, basically build an Ethernet sensor. We do a lot of Ethernet sensors because Ethernet's the right bus for industry. I mean, it's, you know, everyone can connect it, and it's stupidly simple, and you can do remote maintenance and whatnot. And yeah, guess it's not hard real time, but most stuff doesn't actually have to be hard real time, at least on the monitoring side of things. I mean, yeah, okay, sure, if you're running a motor, then maybe, but yeah. So if you guys have any specific requests or want to see something else besides an Internet Ethernet device, then that's what we'll make some suggestions. Otherwise, we're going to do an Ethernet device in 2 weeks, and we're going to finish this design next week. So tune in next week and like and subscribe and all that kind of stuff, because I have no idea how the algorithm works, but since other YouTubers always say to do that, it's probably important.
Take care, guys, and have a nice weekend.